Hello, welcome to our channel. So here at MCA we do a lot of work with mercury, and that's a liquid at room temperature. We know that it amalgamates with most metals, but we've noticed that it behaves really differently with aluminium. We get this kind of off-white fluffy material literally growing out of the aluminium. So what we wanted to do was try and video this happening as time lapse and try and get as much to grow as possible. But that wasn't quite as straightforward as we'd hoped for. So what we're going to do first is show how we got the best result we could, and then show the growth of this weird material coming out of the aluminium. So usually a metal will dissolve in mercury by a process called amalgamation, and the resulting alloy is called an amalgam. Now some can be really useful. For example, gold can be extracted from its ore by a process of amalgamation, and older silvery teeth fillings are an amalgamation of mercury and silver. The only metals that don't form an amalgam with mercury are iron, platinum, tantalum and tungsten. So some warnings before we really get started. We've undertaken all of this in our lab. We've been really careful and safe about things. Mercury is a toxic metal like an awful lot of the heavy metals, but it's the vapour that comes off it that is really hazardous to us. It's where we get the phrase mad as a hatter from. We also use sodium hydroxide, and that's corrosive or caustic and will cause burns to the skin if you come into contact with it. So this isn't really the sort of stuff to be retrying at home. That's why we've done it here in the lab. So to start with, we're going to show what can be thought of as typical amalgamation between mercury and another metal. So what we've got here is a really thin, high purity piece of copper foil, and that's shown on the left-hand side. And we put some mercury over it, and we covered it up. You need to cover it because mercury is actually rather toxic, especially the vapour that comes off of it. And we left this undisturbed for 5 days. After 5 days, we removed the copper from the mercury, and we can see that the section of copper that had been in contact with mercury completely disappeared, so it's dissolved in the mercury. We can also see that the mercury is changed around the edge. Normally mercury forms a droplet on a smooth surface because its contact angle is actually really high, about 130 to 140 degrees. But during the process of amalgamation, the contact angle of mercury changes, it falls below 90 degrees, and we can see around the edge it becomes wetting. It now looks more like molten solder. But with aluminium, things are really quite different. We get this off-white powder forming around a piece of aluminium. We can see a blob of mercury in the middle here with white around it. But this takes quite a long while. This photo was taken after 3 days exposure. But we've found that we can try a few things to promote this, to get it to go a bit quicker perhaps, but certainly to a greater extent. So using high purity aluminium and etching the surface of the aluminium really helps. So we'll start with the etching step. The idea of etching was to create channels and pits in the surface of the aluminium foil. And this would give an increase in surface area of the aluminium, and so greater contact between it and the mercury, and hopefully this would promote a faster reaction. We chose to use chemical etching using a molar solution of sodium hydroxide, and we submerged the aluminium foil in this for 2 minutes. And the chemistry of this is that sodium hydroxide reacts with the aluminium to form sodium aluminate, and that's soluble in the sodium hydroxide solution. So this is filmed in time lapse over a period of 10 minutes. The aluminium we used for the mercury experiment was removed, washed and dried after 2 minutes, but here we're going to leave it for a bit longer. The bubbles forming are hydrogen gas being evolved according to the chemical equation on the last screen, and after 10 minutes the aluminium completely dissolves. So now we'll have a look at how we undertook the exposure to mercury. It's quite a radical way of doing things. The instrument we used is shown here. It's called a mercury porosimeter, and it's used for the technique of mercury porosimetry. The total analysis time, so the total exposure time of aluminium to mercury, is around about 2 hours, and during this the sample's enveloped in mercury and pressures increased to 60,000 psi. bearing in mind atmospheric pressure 14.7 psi, that's around about 4,000 atmospheres of pressure. This technique normally is used to tell us all about the porosity of a sample, the volume and the size of pores present, and it's really, really important to many different materials and applications. One really important application is battery technology, where the porosity of an electrode influences its performance. But battery electrodes are quite commonly printed onto a metallic foil, either copper or aluminium, and that's why we became interested in all of this in the first place. So we used two pieces of foil measuring about 1 centimetre by 2 centimetres, and after the analysis it's all sealed up with the mercury in this, which is called a penetrometer. Now the critical thing is aluminium and mercury don't start to react until they're exposed to oxygen and water vapour. So whilst they're sealed up in the penetrometer, there's neither oxygen nor water vapour present. But as soon as we open it up, then the reaction can start. And we found that an etched aluminium foil of really, really high purity gave a really, really quick reaction. So what we did was we videoed that time-lapse over 90 minutes. So after we'd unloaded the aluminium foil from the penetrometer, we videoed this time-lapse over 90 minutes. So on to the chemistry of it. What's actually happening here? What's the reaction between mercury and aluminium, and what's the white material growing up from the aluminium? Well, this is what we think. Aluminium is a really reactive metal, but it's protected by a thin oxide layer on the surface. That's aluminium oxide or alumina. Now that's not very reactive at all, so it protects that bare metal underneath. Mercury and alumina don't react. But if mercury can break through that oxide layer and contact the pure aluminium underneath, then amalgamation can start. And this is really helped by the porosimeter, which is forcing the mercury into that oxide layer. But aluminium is only really slightly soluble in mercury, so not an awful lot dissolves during amalgamation. But thermodynamically, it's preferable for aluminium to exist as aluminium oxide rather than stay in solution with the mercury. So the process seems to be, as mercury contacts the pure aluminium, amalgamation starts, but this is limited by the low solubility of aluminium in mercury. The aluminium dissolved in the mercury then reacts with oxygen in the atmosphere to form aluminium oxide. It's not entirely clear, but this may also require water vapour to get it started. As the dissolved aluminium forms the oxide, more aluminium from the foil can then become dissolved or amalgamate with the mercury. And the process of dissolution followed by oxidation continues, and the oxide growth continues, pushing upwards from the aluminium surface, as we can just see in that video. So the off-white fluffy material is aluminium oxide. Well, thanks for watching. We tried lots of different aluminium foils before finding this one. It reacted quickly and gave lots of growth. Our next step is to identify the exact phase of this white material, but we need to grab hold of some X-ray diffraction for that. But finally, a quick note. All of this was conducted safely within our lab. Mercury, like most heavy metals, is toxic, especially the vapour that comes off of mercury. Just have a look at the saying, mad as a hatter, and you'll see the effects on the human body. And sodium hydroxide is caustic. It does cause burns to the skin if you spill it. So not the best thing to be retrying. Thanks for watching.